This is the Fields Homework Booklet, question number 15. Explain what is meant by the gravitational potential at a point in a gravitational field. This is a definition that you must learn and be able to express carefully. There were 2 marks allocated to the question. So, first point is to say that gravitational potential is the work done per unit mass. And this work is done when a mass is moved from infinity to that point. You may remember that gravitational potential is 0 at infinity. Another consequence of this is that gravitational potential values are always negative, since you must do work to move the mass from any point to infinity. Next, you are given some data relating to the Earth and the Moon, and we're considering the concept of gravitational potential at the surface. So we have the mass of the Earth expressed as 81 times the mass of the Moon, the radius of the Earth as 3.7 times the radius of the Moon. And we are told the gravitational potential at the surface of Earth is minus 63 megajoules per kilogram. So we need to use this data to find the gravitational potential at the surface of the Moon. So we're relying on using the ratios given here, and we haven't got data that we can just simply put into the equation for gravitational potential at the surface of the Moon. That would be this equation here. So the potential at the Moon's surface is minus g times the mass of the Moon divided by the radius of the Moon. However, we can express the mass and radius of the Moon in terms of the mass and radius of Earth. So doing that, we keep our constant, minus g here, and the mass of the Moon must be the mass of Earth divided by 81. So that's the top line of this fraction. And the radius of the Moon, looking back at the information here, must equal the radius of the Earth divided by 3.7, which we have here. Now, the useful piece of information that we have is the gravitational potential at the surface of Earth. So we're going to want to try and compare the Moon with that situation. So here is the expression for the gravitational potential at the surface of the Earth. And if we look carefully at this new expression, we can see this hidden within this expression here. So pulling out the constant, the mass of the Earth and the radius of the Earth from here, we are left with a factor of 3.7 divided by 81. Notice we have 81 on the bottom of a fraction here. We're dividing by another fraction which would end up being turned upside down. So we are multiplying by 3.7 and our e stays on the bottom. So now we have got this factor and we can multiply our potential at the surface of Earth by this fraction here, leading us to an answer of minus 2.9 megajoules per kilogram. Finally, a graphical part to this question. So sketch a graph on the axis below to indicate how the gravitational potential varies with distance along the line outwards from the surface of the Earth to the surface of the Moon. Now it's worth considering these 2 contributors separately first in your mind, and then try to imagine how the 2 potentials will add together. Now, remember that potential is a scalar quantity, so if we want to find the potential due to two particular sources, you just add up the values, and both of the potential values that you're adding are negative, and so all our answer is in the negative part of the graph here. So first of all, the Earth with its much larger mass would have a curve showing gravitational potential falling with a 1 over r relationship. So you're following the equation V equals minus gm divided by r. Now, because of the much greater mass of the Earth, that in practice is going to lead to a much greater range for this potential before it comes close to zero. Remember, it mustn't touch the zero here because it will only be zero at infinity. But it will follow the 1 over r relationship as you've practiced sketching before and fall fairly quickly to low negative numerical values. Now, the moon, you did actually look at comparing the potential to the potential at the surface of Earth, and if you look back up you see your value that was minus 2.9. So if this is minus 63, then this value here is minus 2.9. So if anything, I have enlarged the scale slightly to reveal the shape. And this potential is going to fall off again with a 1 over r relationship, but because it's starting so much smaller, you would be expecting it to reach very small negative values, much closer to the moon than the Earth's potential does to Earth. And so just imagine two curves overlapping and then think about adding those two together. You'll always have a negative value, and only here will the moon have a very slight impact on the shape of the curve from Earth.